friends, we're back. We're doing a combined loading problem today. What are we going to do? We're going to do this little beam over here. Okay, we've got a loaded beam. And what we're going to do is we need to find the state of stress at point A and B. Point A on top of the beam, point B on the bottom of the beam. When you get a problem like this, the first thing I want you to do, now we know the cross section of this beam. It looks like that, okay? But the first thing I want you to do is think of an attack strategy. How would I solve this, okay? So here's what I'm seeing to solve this problem, okay? Step one is a statics problem. Find global equilibrium, okay? That's first step. Then after that, what am I going to do? I'm going to section this beam in half right here, right? And every time you cut the beam, you must have a M and V, right? Remember that? Okay, so number two, I'm going to section the beam. And I'm going to find M, N, and V, right? If I do that, then what's the next thing I need to do? Then I'm going to try and calculate for stress. I got to calculate bending stress. Looks like I have some bending stress here, some MC over I, right? So I'm going to need, for that, I'm going to calculate I, right? I got to find that. Ooh, to find that, what do you need to do? I got to find the centroid of the thing, right? Because that's where the neutral axis of this thing is. And then once I do that, number four, then I can evaluate stress, and that's going to be sigma stress, and we may have some tau stress, okay? So we got to evaluate that. And remember, each force can cause this, right? It can cause P over A stress, can cause MC over I stress. Those are both sigma stresses. And then for tau, it can cause VQ over IT, right? Transverse shear, or TC over J, which is torsion. Now, in this particular problem, I don't think we're going to have any torsion, so that guy there is going to be not in use, okay? So that's kind of my attack strategy that I'm going to have to do, because what they asked me to do, find state of stress at A and B, A being on top, B being on bottom, right? So if I look at this cross section, A is like up here, and B is way down there, okay? Draw the stress elements, and note that the pins, these pins here, are on the neutral axis of the beam, okay? So let's just start off with the statics. That's something we're good at, right? Let's just find what's going on at C and E. But more importantly, if I'm going to section this in half, I really just need to know what's going on at C, don't I? Okay, so let's just draw that top beam up here. Okay, what do we got? On this end, I have what? A pin connection. I have a CY and a CX. Over here, what is DE? What is that? That's a two-force member, isn't it? What's a two-force member? Pin connected at both ends, no forces or moments in the middle, right? There's nothing else on it. That's a two-force member. So I think with all that load on it that it's going to compress this guy, and a compression member is going to be pushing on me, isn't he? We'll call him FDE, okay? We're missing one thing, aren't we? We're missing this distance right here. You know what? That looks like about 10 feet to me. Let's just make one up. What the heck? That's what you can do. You can just make stuff up, okay, when you're practicing, right? All right, so that's 10 feet all the way out to the end there. Okay, so let's see. What is this angle right here, gang? That makes a triangle that's 12 here and 15 there. So let's see, this angle right here is what? 12, clear, 12 divided by 15, and then inverse tan of that, 36.8, 38.6, 38.7. So this is 38.7 degrees. Okay? That's good. What else is acting on that beam? Well, I've got this distributed load, which is what? 15 feet wide times 1.8 kips per foot, which means that there's a total of 27 kips acting on that beam, right? Okay, what does that mean? Let's see. I think that CX is going to have to go that way because this one goes that way. And CY probably goes up. Okay? So sum of the moments at point C is what? Should we break this guy into components? I see a vector at an angle. This is FDE sine 38.7. This one is FDE cosine 38.7. Okay? So I've got that guy, which rotates me negative. No, it's positive, isn't it? FDE sine 38.7 times how far away? Well, it's 15, isn't it? Okay. And then what else? I got 27, which rotates me. That's negative. Minus 27 times how far away is that? Okay, remember the 27 acts in the middle of that rectangle, right? At the centroid of that rectangle, which is half of 15, which is 7.5, isn't it? Okay. And then that's it, isn't it? Okay, so what is that? 27 times 7.5 equals, divided by 15 equals, divided by the sine of 38.7 equals 21.59. So FDE, 21.59 kips, right? Okay. Then we can do this, the sum of the forces in the x. And what do we have in the x direction? We have this guy, 21.59 times the cosine of 38.7, right? Times, or minus this guy, right? Minus cx. Well, if we move cx to the other side, that just becomes an equals, doesn't it? So 21.59 times the cosine of 38.7 equals, there it is. So cx is equal to 16.85. Okay, there's that guy. I need him, but I also need cy, don't I? So let's get him. Sum of the force in the y equals, okay, what do we got in the y? We got this guy going uphill. So that's 21.59 times the sine of 38.7. Okay, I got this guy going uphill plus cy, and who's going downhill? That guy, minus 27. So cy is equal to, 27 minus 21.59, uh-oh, I forgot the point, times the sine of 38.7 equals 13.5. Okay? So now we got, and that's kips again, right? Kips. Okay? Kilopounds. Kilopounds. All right, we know CX and we know CY. Okay? So we got over here now, or over here, we know these two guys. CY is what? 13.5. And CX 16.85. Okay, are you with me so far? That was step one, right? Step two, let's chop the beam in half. Wha-cha! And let's redraw that, okay? So I'm going to chop the beam at point AB there, which is right there, okay? Let me get rid of all this, okay? here's where I chop the beam, right? And every time you cut the beam, you must have a M and V. Here's N, here's V, there's M, according to the positive sign convention. You remember this stuff back from statics days? Okay, now I know these two numbers. I got them written down here. So let me erase where we came up with those two numbers. Get us some room again. Okay. All right, gang, here we go. Next step. Okay. The next thing, oh yeah, don't forget that this does have a little bit of the distributed load on top of it, okay? And the distributed load just goes from here to here, right? So it's just this area there, right? So how big is that distributed load? Well, it's 5 times 1.8. Oh, I put 1.5. 8. That's 9. So here you go. Whoop. 9 kips is that little portion of the load that's on my beam there, okay? So what is N going to be equal to? N is equal to 16.85. Okay? Kips, right? Now, question for you. Is that section of the beam, if I'm a molecule inside of that beam right there, am I in tension or am I in compression? I'm in tension, right? This thing is pulling on me, isn't it? Right? So remember, when I go to find P over A, that's what I'm going to use for that, right? That's what I'm going to use this guy right there, okay? I'm going to use him in a minute. What about V? How about this? Sum of the forces in the Y. And what do I have in the Y direction? I have minus V. I have plus 13.5. And then I got minus 9. Okay, so move the V to the other side. V is equal to 13.5. I already know what that is. On why am I putting this in my calculator? Minus 9. 4.5, of course it is. Okay. So now I know N, and I know V. I'll use V right here for transverse shear, won't I? For VQ over IT. You know what? I need that M too, don't I? So some of the moments about C, and I'm going to call C, not that C, this is CUT for cut. Okay, I'm taking the moments about where I cut it in half right there. Because if I do that, I'll knock out N, I knock out V. You can't knock out your MA, so the M needs to stay. And that's a what? That's a positive M, isn't it? Okay? And then the 9 rotates me positive, so plus 9 times how far away? Well, the 9 sits halfway, right? It sits halfway on this. This is 5. So the 9 is 2.5 away. And then the 13.5 rotates me, whoop, that's negative, minus 13.5. But he's 5 away, right? It's the whole 5. And then, of course, CX, that's a cha-cha force. Wha-cha! He goes through point C. He's knocked out, does not contribute to the moment. That's all we got. So M is equal to, here we go, 13.5 times 5 minus 9 times 2.5 is 45. And what is that? What units is that? That's kip-ft. Be careful and track your units, right? Man, how many times in solids have I told you to track your units? About 10,000 times so far this whole series? And are you still not doing it? Ugh. Okay, there we go, gang. So now we know M, N, and V, right? We did step 2. Step next is the thing we thought about. We need to go back over that cross section and we need to find the neutral axis of that thing, okay? How do we do that? Well, here's how you do that. Always make the bottom of the part your datum, okay? And that way all of your values are positive when you're figuring the centroid. So I'm just going to divide this across right here, okay? And I'm going to call this shape 1 and I'm going to call this shape 2, okay? So I've got shape 1, I've got shape 2. And what am I looking for here? What are we looking for? We're looking for this. Let's draw it in a different color. Okay. We're looking for this. Golly, that lid is on there. Okay, here we go. What the? In A. We're looking for where is the neutral axis, okay? Where is it? Okay, so what we're looking for is this. Whoop. Y bar. All right, that's what we're looking for. So we need a Y, we need an A, and we need a YA. Whoop, whoop, whoop. There you go. So where's Y for piece number 1? Well, it's half of 6. That's carry the 9, that's just a 3. And then the area is 1 times 6. Well, that's a 6. 3 times 6, that's 18. This stuff's easy, isn't it? Okay, where's the centroid of piece number 2? Right there. How do I get there from my datum? I got to go 6 and then half of 1.5. So that's what? 6.75. So what's the area of that piece number 2? 1.5 times 7, right? 1.5 times 7 is 10.5. And then, I can't do that in my head, times 6.75 is 70.875, 70.9, okay? And then what? Add these together, plus 18 is 88.9. And then this guy is, I can do this one, 16.5. And then Y bar is the sum of the YAs, which is 88.9, divided by the sum of the A's, which is 16.5, which means that Y bar is at 88.9 divided by 16.5, 5.38, 5.4. Let's call it 5.4. Okay? So much rounding here, Dr. Hanson. It's 3875. Okay, give me a break. We'll call it 39. Okay, all right, you talked me into it. There you go. Okay, so this Y bar right here is 5.39 inches. Okay. All right, so let's calculate I. Okay, I XX is equal to. Okay, we got to use the parallel axis theorem, right? 1/12. The base of piece number 1 is 1. The height of piece number 2 is 6 cubed. 1/12 BH cubed, remember that's for a rectangle, plus the area of piece number 1, bam, right there, 6 times D squared. What is D? Remember, this works every single time. Take that number, 5.39, subtract that number from it, which leaves you with 2.39, okay? That's piece number 1, so plus, here comes piece number 2, 1/12. The base, what's the base? 7, because it's all about that base, about that, times, what's the height? 1.5 cubed plus the area, this time 10.5 times D squared. What's D squared? This still works, okay? 5.39 minus that number, 6.75. Bam! 1.36. It works every single time. Remember, what is D? D is the distance from the neutral axis to the centroid of the piece part. So what else would work on this is to go from the neutral axis, measure to the outside, and then subtract back 0.75. It gives you the exact same number, okay? Okay, now y'all got 10 chances to put this in your calculator and get this number right. No way. No way. Let's see if we can do this. Let's see. 6 cubed equals, divided by 12 equals, plus 6 times 2.39 squared equals 52.27. That's a 52.27 0.27 plus, what's the bottom one? 7 times 1.5 cubed equals, divided by 12 equals, plus 10.5 times 1.36 squared equals 21.39. 21.39. And so those two added together plus 52.27. 73.66. Okay? And what units goes on that, gang? Inches to the fourth. Inches to the fourth. Okay, so there's my I. Okay? So let's write all this down up here so we can get some room. So N is equal to 16.85 kips. V is equal to 4.5 kips. M is equal to 45 kip-ft. I is equal to 73.66 inches to the fourth, okay? Let me erase my board. Okay, now, really and truly, think about it for a second. We've done a lot of work already, right? We've done a lot of work. But really and truly, everything that we've found so far, which is all of this up here, every single one of those things you learned in statics. We haven't done any solids yet. That is, we have just completely done statics problems so far, okay? It's time for the mechanics of material stuff. All right, here we go, okay? Now you need to think about a couple of things here. Number one, let's think about in our mind, if this thing was going to be on here, this load was on this beam, what's going to happen to that beam? Because it's important to kind of think about that. What does that beam look like after that load has been on it? I would propose to you that that beam is going to be doing some sagging. Okay, like that, right? You see how much it's sagged down? Because it has that big load on it, doesn't it? Okay? Now, since it's bending like that, because gravity sucks, right? Just pulling down on me all the time, gravity. Why do I need to know that? Well, here's what I need to know. Point A, which lives on the top of the beam, is point A going to be in tension or compression? Remember, if I'm finding normal stress, compression I call a negative, and tension I call a positive, don't I? So if I live on the top of the beam, what do you think? I'm being compressed. If I'm on the bottom of the beam, I'm being stretched. So point B is going to be in tension from bending, and point A is going to be in compression from bending, okay? So that's an important thing to kind of remember there, okay? So let's start off with sigma stress, okay? So we got two things. We got sigma about point A, and we got sigma about point B, okay? Now point A and point B, as far as the P over A, right? As far as that guy goes, both of them live inside of this beam that is being stretched, right? So both of them feel the exact same P over A force, okay? And we really shouldn't call it P because P sounds like pressure. We should really call it N over A, right? Instead of P over A, we should call it N over A, the normal force. Well, okay, do we know that? Yes. 16.85 kips, that's N, isn't it? Right there, divided by A. Oh no, I erased A. I remember it though. It was 10.5 plus 6, which is 16.5, wasn't it? We just figured that up in the last step, didn't we? 16.5 inches squared, okay? Same guy for this guy. Okay, he's feeling the same N over A. Okay? Kips per square inch, or what we call KSI, okay? Why are both of those guys positive? Because they're both in tension. What does tension start with? A positive sign, right? Okay? Now we do the MC over I. Now here's the deal. For point A, on top of the beam, we said he was going to be in compression, right? So that compression guy is going to be a negative. The tension guy is going to be a positive though, isn't he? Okay? So MC over I. M is 45 kip-ft. Are you concerned? I'm concerned. What is feet doing in there? We got to have everything in inches, okay? So let's get rid of that. Let's put a feet on the bottom and a 12 inches on the top, and that'll get rid of that guy, right? Okay? Times C. What is C? C is the distance from the neutral axis to the point of interest. Well, if it's 5.39 from the bottom of the part to there, right, then how much is it from there to the top of the part? Where are you, calculator? Okay, here we go. To the top of the part, the whole part is what? 7.5 tall? So 7.5 minus 5.39 is equal to 2.11. So this distance here, 2.11. Okay? So C, the distance from the neutral axis to the point of interest, which is point A in this case, is 2.11 inches. Divided by I, hey, we just found that, didn't we? 73.66 inches to the fourth. Okay? There's that guy. Now this guy is in tension on the bottom. Okay? So he's 45 times 12. But what's his distance from the neutral axis to the point of interest? So from the neutral axis to him, 5.39. Divided by I, 73.66. Okay, now we need to do is crunch those numbers, and we're there, right? Let's see if we can do that. 16.85 divided by 16.5 is 1.02. So this is 1.02, this is 1.02, okay? And then 45 times 12 times 2.11 equals, divided by 73.66 equals 15.47. Okay, so 1.02 minus, second, answer. That top one is minus 14.44 KSI. And then this one is, what is this guy? 45 times 12 times 5.39 equals, divided by 73.66 equals 39.51. Okay, plus 1.02 equals 40.53. Okay, so that right there is the sigma stress, right, in the x direction for both of these guys, okay? So this right here is going to be sigma x. This right here is going to be sigma x. But this is for point A, that's for point B, okay? So when we draw our stress elements here in a second, we're going to use those, okay? So how about this guy? Tau A, tau B, okay? Oh, man. VQ over IT, okay? Can we do it? I think we can. Okay. Oh, this is going to be easy, isn't it? This is going to be quite easy, isn't it? Because why? Do we know what V is? Yes, we know what V is. It's 4.5 kips. But what is Q? What is Q for point A? How much area is above point A? None. How much area is below point B? None. What does that mean? That means that Q for point A equals 0. Q for point B equals to 0. And so guess what? Remember that. Shear stress is maximum at the neutral axis and 0 at the outside of the part, whereas normal stress is maximum at the neutral axis and, no, backwards, is normal stress is 0 at the neutral axis and maximum at the outside of the part. So those two are backwards from each other. So therefore, tau A equals 0, tau B equals 0. And there's no torsion. There's no TC over J. So this is not too bad, is it? So the stress elements, what are they going to look like? Here's stress for point A. Here's the stress element of point B. Okay? Point A was what? Negative. What does that mean? He's in compression. 14.44 KSI. This guy in tension. Positive answer. 40.53 KSI. Whew. Okay. We got it. All the way to the end. Are we good? All right, that's combined loading. Another example problem for us. Hope that helped, and I'll see you on the next video.